So we have, I think, about 70 people watching online, so now they can see what's going on. So again, welcome to Tackling Machine Learning Complexity for Data Curation. This is our first webinar event at the Data Hub, and I hope you enjoy the space. So as I was mentioning, ODX is an organization that was formed to help people, or help companies commercialize using open data. So we work on both sides of the demand and supply coin. On the supply side, we're working with different levels of government, helping them build their data programs to help them deliver the data to companies. And on the demand side, we're working with companies, helping them find access data. So without further ado, I'll introduce you to our speaker for today. Please welcome Ihab Ilyas. He's a professor at the Cheriton School of Computer Science at the University of Waterloo, and also the co-founder of Tamr, a startup which focuses on large-scale data integration.
Thank you, everybody. Thanks for showing up. Thanks for being online. Today I'm going to talk a little bit about a hard problem that is not very pleasant in the space of data, which is data curation, data cleaning, data quality. And although you're going to see the word machine learning, it's not going to be about analytics, which we're used to do. So this is probably one of the few talks that you're going to see where machine learning is used to clean data that is used in machine learning. So we're using machine learning in a little bit earlier stage in the data curation process. So I'm going to go ahead and introduce that to you today, and I'm sure that we're going to be open for questions, but do interrupt me if I miss them. So data curation is unfortunately the most time-consuming and least enjoyable job. It's the nightmare of most data scientists. In any data analytics project or data science project, this is 90% of the time. 60% of the time is around pure cleaning, but 90% of the time is in the area of data prep. And it's not uncommon when people spend months and months trying to get their data together, curate it, build it, transform it, put it in the right format, all the way till they can shove it downstream to where the pretty pictures can come up at the end, and then you can show your predictive analytics and all the great stuff that you can see, that the CIOs and CEOs can see. So why it's an ugly problem and why it's not been tackled so far? It's because we're not really sure what it is. I mean, there are many definitions for data curation, but it's mostly janitorial work around data. It's mostly a bag of tricks, arts more than science, because we just want to extract value from massive amount of data, unstructured, structured, JSON, XML, pure tables behind Oracle databases and others, but also streams and other things. And it's not as easy as we get our head around, for example, relational databases. When we start to build platforms and others, data curation is a little bit more challenging just because how open it is, how the variety of the data kills us way earlier than when the volume of the data kills us. So I'm going to tell you a little bit about some of the technical challenges around data curation or data cleaning or data integration in general. Don't worry about the naming for now. And then I'm going to tell you about some practical issues, pragmatic issues that we often missed in academia and also in industry for a long time. But the good news is that there is a wave now of new effort from the big elephants and also from the startup community to start to solve that problem. So here's an example of data curation problem, a very dear problem to our heart, especially my students, because we have lots of papers in that domain. That's called schema map. And schema mapping, you have a bunch of sources, and there are some structure that describe what's in a specific source in terms of common names, if you like the knowledge around or the schema around that source. And oftentimes we describe things differently. So first name and last name in one table might be name in another table. Part number in one table might be part and a hash sign, or in a different language, or even foobar or column one. And you know what it is. And the schema mapping exercise is as easy as find correspondence between columns such that it can map to each other and ultimately can map to what we call a global glorious schema where most data curation people started with. That you design a global schema, that's how things should look like in the enterprise, and then we map anything that we have to that global schema. It worked for a while where these sources usually were in the tens. The biggest success in data integration was done by hand, by actually people curating this. But for automatic curation, we failed miserably because it's a semi-automatic process and it doesn't scale. So the bad news is people started to need this for hundreds of thousands of sources a day. Think about pharmaceutical companies where their scientists send tables or assays or sources from all over the world when they do clinical study on a drug. Now, sending those to the headquarters, they need to integrate all these sources to make sure first they talk about the same thing and describe the same thing in the same way. The mirror problem of that problem is what we call record linkage or data deduplication, and it has so many other names. But it's the same problem but on data. Within a source, how do I know that the same entity is not represented more than once? So it's a classical problem since the 60s and even earlier when the Census Bureau started to count people, and now for the same record, for the same real-world entity, there are many records that are describing the same person. So that deduplication process requires us to identify that this representation of an entity and this other representation that can be very different on the surface are representing the same entity. And again, the problem scales well in general, but I'm going to tell you about a difficult problem there. But there are other many problems as well. And one of the most notorious problems is what we call the problem of null or missing values in data. And if you work with data, you will see that this is a real problem. Whenever I get a new data source, you don't know everything about that data source. And what makes things worse, that in academia, we have been dealing with this from kind of logic point of view, and how to deal with things that we don't know and the representation of nulls. But the reality is nulls don't even exist in reality, in practice. What exists in practice is all sort of representation of I do not know, like 9999, 7777, Paul Joe, come later, dollar signs. All of that are sometimes legal values for that column, but represent nothing. This is my favorite example where you think about spending time in a place, and these are pretty pictures that you got from Google, and say, I'd like to spend time where these things are. So where are they located? So as a data scientist, you're gonna get the geolocation of these things, you're gonna put it on a map, and hopefully that will dictate your next location so you can actually see all these places. But if you did this automatically, it would map to this peculiar, beautiful island here that have all these pictures. That's what Google will tell you. And the problem, if you book a flight, you're going to end up in that place, which is what we call the zero island. This place has something in common with everything in the data. It has the geo location of 0, 0, or null, null. So anything that I do not know would be in this critical island. So do not spend your vacation on the null island. It's not that. So there are more technical problems around this. So these are kind of easy to spot, but there are other problems that we spend a lot of time in academia and industry trying to solve it. And this is one of these problems that is hard to spot by a naked eye. So it looks like a legitimate table. It has Anne and Mark White and Mark Lee and John Smith. So no duplicates, no missing values. Things seem okay. But if you look carefully, then there will be things like these business rules, forget about how it's written, but this rule basically tell you you cannot be an employee of a manager and you're making more than your manager. Well, we know it's not true because we know a lot of special cases. But if you look carefully, then you will find violations of this rule because Mark White and Mark Lee, both of them have the same rule, for example. Sorry, this one was about living in New York City and need to be compensated more. So if you live in New York City, you should be making more than people not living in New York City to compensate for living expenses. And Mark White and Mark Lee are in the same role, but White is making more salary and he is not living in New York City. So San Jose cannot be making more than New York City for some reason. So something is wrong, but maybe they are not in the same role. Maybe the salary is wrong. Maybe Mark Lee is not even in New York City. So the fact that there is a violation and contradiction doesn't mean that you know where the error is. And that's what this picture. Okay, so what is data cleaning? Is to take all of these signals into account and start from a benign looking table like this that is full of false data and incorrect data, and start finding duplicates, find value and syntactic errors, some missing values, identify integrity constraint violations. For example, these are two people living in two different cities but in the same zip code, which we know is impossible. And the repairing part of data cleaning is to actually transform the data by consolidating records and correcting values and imputing these missing values, and maybe using machine learning, and so on. So why this is hard? And why machine learning is at the heart of it? I mean, not surprisingly, the scale doesn't allow us to look at all these problems by hand, and we need to teach a machine to learn about how to find these errors and hopefully suggest not only possible errors, but repairs for these errors. And I'm going to give you a very quick overview about three main efforts or three technical challenges that have been tackled heavily in industry because there is value for this. Record matching and schema mapping, which is something that we do in Tamr all the time, and by just these two simple problems, by just solving them at scale, we solve massive problems for the enterprise, and these are hundreds of millions of dollars savings a year. It's as easy as this. By integrating all the ERP systems so you don't overpay for a part. Integrating all your policies so you do not overcharge your customer, you can get more customers. By just getting that right, you can get a massive ROI on your thing. But two upcoming efforts as well, that is when we get comfortable with machine learning and machine learning pipelines, we're now being able to find missing values or suggest repairs for missing values, but also repair hard constraints and business logic beyond just schema matching and DB. So let's start. What is record linkage? Let's dive into this problem very quickly. I would like to find duplicates in this table. That's what I want. So what is the first thing that you're gonna come to your mind? Well, I start comparing things to each other. So if I can come up with kind of a matrix or an edge between every two entities, and I can assess how close they are, it's a good start. So for example, from that, I'm going to represent this small graph where every record is a node, and an edge is the similarity between two records. And if I do this, then it's a good starting point to understand what's close and what's not close. But it's not enough, because that process that we just did is not transitive. So for example, P1 is very close to P2, P2 is kind of close to P5, but P5 is not close to P1. And we know that that's not okay in reality. If P1 and P2 are the same, and P2 and P5 are the same, P1 and P5 have to be the same, because they are the same person, or the same entity. So we need another step, which we call data clustering, which is also something that you probably know a lot, with all these clustering algorithms. And the idea is to use these input signals of similarity and come up with clusters of the same real-world entity. And if we manage to do that, then we are almost done, and the problem, in terms of scale at least, becomes minute, because I need now to focus on every cluster and come up with a representation of the golden record in each cluster, which we call entity consolidation. And if I can do this, then I cleaned or curated that table. Think about this table as the union of all your ERP systems, and this output table is like only one record per supplier part, for example. And you consolidated all these duplicates in your data, so you do not have 6 representation of glass or 7 representation of a gasket and so on. Why this problem is hard? What is the first thing that you can see here? Even this step is super hard. It's not super hard to come up with a similarity, because we spend tons of papers on coming up. Cosine similarity, Jaccard similarity, even machine learning models that can learn from some training data and will tell you the probability that two entities are matched. The problem in this picture is the n-squared complexity of this data. So for 10 records, you need around 55 comparisons or 45 comparisons. 100 records, you need in the order of 10,000. It's n-squared. So for a million records, you need 1 to the 12. You need massive amounts of comparisons. And a million record is a tooling with respect to OLTP data and the type of data that people get every day. So if you spend your time just getting this matrix, getting just the edge similarity, all the similarities, pairwise similarity, it's a no start. You're going to fail miserably, because you just cannot have the power. And it is, by the way, embarrassingly unparallelizable. So while we're all fond of Spark and the new Hadoop and all the big data kind of infrastructure that allowed us to do things that we couldn't do in the past, I need to compare everybody to everybody else. And if you work with Spark and something like that, it means shuffle and reshuffle and shuffle and reshuffle, which will kill you as well. And if you solve that problem, clustering is a black magic, because there are tons of clustering algorithms. Each one of them have a very different objective function. Do you use correlation clustering and minimize disagreement? Do you use agglomerative hierarchical clustering? Is it single linkage, or is it is k-means, or what do I use and why? Also not very understood, but we're going to use, as usual, the first clustering algorithm that I know, and I'm going to play it on this game and see what happens. And if you manage to do these two, the really black magic comes in entity consolidation, because it's purely domain specific. For wages, you probably want to take the max. But for height of the person, you probably want to take the average, because it was recorded at different times. The name, you must want to take, you might want to take the most canonical representation of the name, and so on. So you need to kind of crank your best ETL tools. Today, I'm going to focus on minute problem, which is coming up with this beautiful number here using machine learning, and show you how to scale these machine learning pipelines to do this problem at scale. That's all we're going to talk about today, plus some teasers for things that we're going to talk about. So a simple approach for machine learning here would be to build a classifier, and that classifier will tell me if two records are the same or not. So let's assume that they have a customer table, name, address, phone, comments, last visit date, and what have you. So I'm going to start by looking at instances of this table, and this is C1 and C2, John Smith, Jeff Smith, and so on. And for these two, I would like to understand if they are the same or not. So this is the classifier that I'm going to build. In order to do this, I need to generate these pairs. So this is a pair of C1, C2, and the feature vector of that pair, or what we call the features of that pair, will probably be similarity functions that you would design. For example, similarity of the name is 0.7, similarity of the address, and in that similarity function, you might use your best similarity function. Cosine similarity for strings, address doctor for similarity in the address, similarity of the phone, your own specific script that kind of take into account the semantics of the phone. What have you, doesn't matter. With these numbers, and now you have this feature vectors of possible similarities, or all the similarities among all possible attributes of that pair. Now I would like to use these features and build a classifier. So for a pair that I haven't seen before, it's easy to generate this in an unsupervised way, because I'm going to just compute it. And if I can teach a classifier how to do it correctly, then I can get, at the end, match or not match. And maybe with a probability of a match or not match as well. In order to do that, I'm going to show this classifier lots of examples that are labeled already. These two are the same, these two are not the same, these two are the same, these two are not the same. Lots of positive examples, lots of negative examples, and every time I'm going to compute these features. But the training phase of the machine learning would be with data, with pairs like those, but with a label. And the deployment version of the classifier will be with unlabeled data that you'll have to label. That's all what we're going to do. In order to do this, I need to answer a few questions. So this is the pragmatic piece of building machine learning, and many of you probably went through this, and if you are curious how to do this, so I'll just try to tell you our personal stories in building these. Okay, well, first off, which feature should I use? Which similarity function? This is the glorious topic of feature engineering in machine learning, where you eyeball the data and see what you should use to train your classifiers. And it's experience, it's a trial and error, and it's so many other things. But with advanced machine learning and these tools, I can try a lot of things. I can get into an exercise when I play with things. And oftentimes, we come up with best practices, if you like, for feature engineering. It's not uncommon for data scientists to do what we call data profiling first, So I get the distributions of this data, histograms, the most discriminative feature. For example, you'd like to ignore a feature that is the same for everybody. That's not going to be very discriminative. Or you'd like to ignore a key that is surrogate key, 1, 2, 3, 4, 5, 6. You know that that's not going to help. By getting rid of that, it might help you with limiting the number of features, because we all know the more features you need, you probably need more training data, and if your training data is scarce, not everybody is Google, not everybody can use deep learning with 200 million cats and dogs labeled and so on. Sometimes your data is not that rich in terms of training data, and you need to do something about it. So tables are usually also heavily normalized, which basically means you need to undo everything your good DBA next door did, because they fragmented the data all over the place to be able to fit it in Oracle and what have you, and you need to collect it back to get all the features that is needed. Because your customer might be just 1, 2, 3, and tons of foreign keys that touch tons of dimension tables, and you have to get these back because you need more signals. Not only that, you might not even be satisfied with the type of data you have in the enterprise, but from the geolocation, you can connect to open data and publicly available data to enrich your record to get as many signals as possibly you can collect to get that correct. Okay, let's assume that we did that exercise and we got it correct. So I labeled 100 pairs for training data. Is that enough? We get this all the time, especially for our first customer. That was the $100,000 question. So that's the case. Can I stop after 100? How about 200, 400? I cannot go like this forever. I need to stop at some point. And now I did all this hard work, and I did this project, and I now have a classifier on table 1. Can I use the same thing on table 2, or do I need to do it again? And in order to know this, you need to probably dive into some machine learning concept that has to do with understanding what your training data will do to your model and how the model interacts with training data. And in machine learning, you probably, most of you know that there are this, as the number of features increase, the complexity of your model increases. That's kind of, you know, like if you have, for example, a decision tree or naive Bayes, and you're using 2, 3 features, it's different than using 100 features, right? So it's a more complex model. But at the same time, overfitting with your training data becomes a huge risk. And the reason is now you probably will not have enough training data to get that model aware of all the cases, if you will. However, if you use little number, or like a small number of features, you're probably going to be biased, and you're going to probably learn from only what you know. And you know, for example, I know everything about people in gray shirts, and people in gray shirts are programmers, and that's the only rule that I'm going to do. And then you're now in a little bit biased. You're probably going to learn a good classifier about people, yes or no, but you're not going to get the big picture. Anyways, I'm not doing justice to this, but I'm not going to dive in it yet. But we need to be careful about how much training data. And unfortunately, it's not a one answer, because it depends on the model, how much training data, and the complexity of the phenomena that you'd like to predict, and so on. So in general, what we find is the reuse of models across projects is extremely hard. And oftentimes we retrain rather than fiddling with the model to see if it's applicable to this or not. So I don't know, think about this as a passing on the advice that we spend 3 months to know it the hard way. Bagging, boosting, and other sampling ways that will allow you to increase the signal that you get from training data is a useful and very valuable tool, especially for the cold start. If I have a small piece of starting data, there are lots of tricks that we can resample and replicate this to get the best value after your training data. There is now also a big trend in what we call weak supervision, where you use rules that you know in the enterprise to generate training data for you to train them on. Well, that sounds a little bit counterintuitive. Like if I have rules, then applying it, you will get some label data, but it's only for these rules. And then if I apply machine learning to learn from what I just did, well, it sounds fishy. You're going to be probably biased because it's not a random sample of the answers. And there is a risk of learning only what you know in terms of these rules. But it's a growing field. We have some contributions. Now I'm going to tell you about at the end of the talk very quickly, how to reason about these rules, how to grow the training data around these rules, but it becomes super valuable tool to get rid of the cold start problem in machine learning. Okay, most pairs I choose are non-matches. This is a peculiar training problem for data cleaning in general, finding errors and duplicates when the data is mostly correct. Then it becomes the rare event problem. If I randomly select two tuples, they're probably not a match. So you're going to get a lot of non-matches, and it becomes looking for a needle in a haystack. And that's again the cold start problem using positive examples from your rules, but negative examples you have to be careful because negative examples are plenty, and you'd like to choose the negative examples that can help you converge faster. Okay, I'm not going to talk about this because when we fix this, we usually screw up the previous thing. Right? We get the data correctly, but we screw up the bias, and we need to work. Okay. Now I got my training data, I got the features. Now I'm ready, and I applied. I downloaded my favorite machine learning development tool, and I then discovered that I have gazillion models to choose from. Should I be trendy and I use deep learning? Should I use SVM because my friend told me about it? Or should I use decision trees because I can show it to people? And what guides that choice of models is an interesting phenomenon that we went through when we talked to customers about using machine learning in general. And customers care a lot, at least our customers care a lot about that question, which is not a machine learning question in the sense of development, but it's more of a psychological question. Do your jazz, but explain why the machine said that these two things are the same. And there are models that you can talk about why they did what they did, and there are models that is harder to explain why. So this is my kind of shameful attempt to try to get like a taxonomy of the explainability of some of the well-known models, for example, and their requirements. Might not be very accurate, but I think it's accurate enough for this discussion. So let's take an example. If I use a naive Bayes model, which assumes independence of features, is very easy to train, then it's not really explainable because you get a bunch of conditional probability about features, and it's hard to talk to people about the independence of these features and so on. But it's a modest requirement for training data. You can get conversions very quickly if you manage to get the feature engineering correctly, which basically makes feature engineering a vital aspect of that process. If you get your features right and they are independent and they are spot on, then with little training data, you get a working classifier, not very explainable, but working. If you go to logistic regression, our favorite, because it's basically killed the need for a heavy feature engineering. You throw all your features in, you use regularizations and other tricks, and the weights will magically appear and will tell you what's important and what's not. But it has a big requirement for enough training data that grows very quickly with the number of features. But at least I can communicate to people the weights of the most important features that I design. So I can tell them things like the machine, choose these two to be the same because they are the same in name, and the name has a very big weight in my model, for example. Something that you can communicate. I'm not sure if it's acceptable, but it's communicable. Deep neural network, and I'm preaching to the choir. If you are in the data space, looks like magic, and that's what we tell people. It's magical, and I add more layers. And when in doubt, I add even more layers, and that solves the problem. But it has an unrealistic demand for training data, especially in the enterprise. I know the big success in the unstructured world. In the structured world, very little success for deep neural network. The reason in the structured world is lots of encoding of the domain knowledge and schemas and metadata and what have you, and not much as labeled data lying around, as in images and text and so on. So bear that in mind. But minimal feature engineering, in fact, you can just stick to representational features and kind of figure out features from features and features that cannot be even explained. Random forests and decision trees in general, people like it, at least because it looks like a rule. So I can communicate it as a rule, when this less than that, and when the similarity is less than this, and the similarity of other fields is greater than that, it's a match. grows reasonably with the number of trees, and it requires some feature engineering. So where are you in that space depends on your problem. But what I'm trying to advocate for is understanding that space is probably your most valuable tool before jumping on a data curation, using machine learning for data curation. So I'm done. I chose the data, chose the features, I came up with the data, I used some rules, I understood bias and overfitting. I also understand my problem, I came up with the right model for it, and I'm done. Well, the problem is this is not a one-time process. And if you talk to people who deploy massive machine learning pipelines, will tell you the biggest problem is this thing in the middle that's called model validation and model verification all the time. Because it's not like you are going to attack a sitting duck of data. You are going to train all of that stuff, and then tomorrow you're going to get a delta, more records, more knowledge, and so on. When my model stops to work? First, validation that the model itself should graduate and work. It's kind of a well understood problem. People use key folding and in-sample validation, out-of-sample validation, other things. But understanding when the model stops to work requires an eye on that model all the time, and an automatic trigger that should fire when it starts to screw up. Maybe I should use many of those. Maybe I should use an ensemble. Maybe I should use an engineer just looking at that all the time. So labeling is a continuous exercise, and training is part of the model. So one of the examples that that show this, that in Tamr, for example, we do not have a training phase and a deployment phase. We have a machine learning model loop, and we train a little bit in the cold start, and then once it's deployed, we continuously label and collect labeling data all the time. So, and that can be by surfacing things that we're not so careful about, so certain about, randomly selecting some questions and getting the user input on it, and also soliciting user input in a non-trivial way on the report at the end, or on aggregates on the data, or in a rule, or things like that, that will allow us to monitor how much change our training data and the underlying structure of the training data, and hence the model. So this is putting all these things together, and this is a simple problem called dedupe, but in order to build a system that works in practice, it has to have all these boxes that are kind of not that trivial, not all of them. So you start by source data, and then you do pair generation. You get all your pairs, you extract all these features and similarity functions, you get that feature vector space, then the machine learning kind of loop. This is waiting for it to be classified. In order to build that classifier, you start by training data, you build classifiers, you have these models, you feed these models to the classifier, or the classification box, and the output is a bunch of labeled data. You can sample from that in an what we call active learning, which is basically looking for, this is usually an ensemble of many classifiers. And when they disagree, we take this data and shoot it to the user to label it more. So there is this sample of high impact questions, if you like, to the user, and the user or the expert, domain expert, will add to this training data. At the end, part of the production, we do clustering, because that's what you want to do. And these are the clusters at the end that I showed you in the beginning. And even that, we validated with the user. And it's interesting how to take an answer from a user on a cluster and translate that into pairs that this model expects. So if I tell you, for example, no, John should not be in that cluster of people, I actually told you a lot. I told you n pairs. Or if these two, I put two things together, like 10 people, I put them in the same cluster, and I told you, no, they are 5 and 5. I actually told you a lot. I told you that these things are the same, these things are the same, and all the bipartite connections are not the same. And all of that should be part of that data. And when you think you're done, we still did not solve the n-squared problem, which I didn't talk about today, because we cannot generate all these pairs. So oftentimes, we don't do this. Instead, we do a lot of locality-sensitive hashing and blocking, and more machine learning to tell you first how to bin the data, how to partition the data, such that the probability that two things across from each other, across clusters or across partitions, should not match. And we do this iteratively. I guess I'm trying to convey to you that in order to shepherd a machine learning pipeline for something like data curation, What hits you very quickly is the scale, the choice of these models, and explainability, because that person over here requires a lot of context to be able to answer these questions and help you proceed with your data. So these are the blocking pieces that I was talking about, but I'm going to skip it. And I'm going to quickly give you an example of another use of machine learning. This is a recent work that just appeared with my friends from Deep Dive in Stanford. Deep Dive has just been actually acquired in the Valley for $200 million by Apple. But that's the open source piece of it. In that new work, we're trying to tackle the data repairing problem. We're allowing the machine learning to take all the signals from everything you know in your data sources. Your deduplication, what I just told you earlier, your business rules, function dependencies, or check constraints, or what have you. And available open data that can act as a guide or as a reference that has something to do with your data. For example, if you're talking about M&As or company data, then there's a lot of open data about these companies and where they are from, and more information in rich data around them. If you're dealing with diseases and scientific data, there's tons of those as well. And the ability to take that and enrich your curation project with open data is a massive value, because the problem is there is usually not enough context to take decisions, even with machine learning. So in that new work, we're taking all of these things and we're trying to compile them in what we call factor graphs, which is, think about it as a big machine learning model or a way to do inference, probabilistic inference. And then we modeled the whole database, the errors in the database as missing values, and trying to ask the machine to infer the most likely value for a missing value. So in probability terminology would be every cell in the database is a random variable. All of these will be signals that will allow you to author these massive factor graphs, and then you run this probabilistic inference till you find the value that maximizes the kind of stability of that system. And it showed great results, and we basically beat everybody else. Still, it's an academic project, but it has great it has a great potential. And the reason is, unlike previous techniques, even using machine learning, it focused more on taking all the signals in. So take that as use all the signals. If you start by a local view of your data, you're probably gonna end up by local decisions of your data. So it doesn't matter how complicated your model is, how complicated your machine learning model is, if you do not have enough data. I'm not talking about data only on the size, but also how rich this is and how it's aware across business units. You're probably going to end up by decisions that are going to be overwritten very soon. I'm not sure how much time I have, but I'm going to end by other data curation problems that that you will hear a lot about soon. So this is textbook business intelligence, if you like, for data. You write extractors and your ETL, and you do transformations and transformations and transformations till you come up with your report-like data. And data, as it goes up in that stack, think about these as Spark workflows or your ETL stack, with a bunch of things written at the shop and some other things by other tools. And as the data flow in that stack, the data gains more and more semantics. So here it's PDF and Word and start to be tables, so I know a little bit about tables. Then I start join them together, then they appear as shops and employees. Then I aggregate them together, then they start to appear as more report that I can understand. And at every level, there are more business logic that you can add to that stack. So the magic word that currently people are worrying about is data governance and provenance. What does it mean? I need to understand at any point where that thing that I'm seeing in my lovely report, where it came from. Because while I can spot errors here very quickly, because the pie chart looks wrong, and that store can never make as much profit as they claim, they don't sell anything. So something is wrong. Unfortunately, you cannot change anything in the pie chart. And I'd like to push it all the way down to see where is the data source that contributed to that error. not only to fix it, but also to prevent it from happening later in a kind of prescriptive way. And in order to do this, we need some machine-readable provenance. We tried this before in a very limited, like across SQL, for example. We know how to do kind of formulas or polynomial that tell you where every tuple or record in the database came from. But the problem becomes notoriously hard when you start to talk across systems. So if you're coming data from your customer or your ingest box, and you know where it came from, and then you wrote some software, you probably can keep metadata to describe where it came from and carry it with you. Tableau, and you generate something out of it, and you don't know that link. And then the output, you get shoved in another tool that does few things, and it goes out, and you don't know that link. And then at the end, all what you know that this is the data source, this data set was generated from all this pool of garbage that are millions and millions of records, and you have to dig in and debug. So provenance and lineage and governance become now crucial to put order in the chaos that we created in data lakes. I'm not against data lakes. I think it's a beautiful thing. I'm all for schema later and getting the data first and then figuring out the transformations later. But the problem that we have, victims of our own success, we overdid it and we shoved too many things in the lake without understanding where they came from. And now we're stuck with that kind of thing. So we turned it into a swamp. Many people using the term. Big fan. So detection and repairing are decoupled, and governance. So there's a lot of work. And people who are after this, a project in Berkeley, a project between us and MIT, called the Civilizer. There are open things from Hortonworks, for example, like governance stacks, basically you can add metadata and so on. Another thing that we often miss in reality is this curation process that I told you about, which is a continuous thing. So this is like a much coarser granularity view of what I talked about, but for general errors. You usually have a bunch of source, you run your analytics, you have your reporting views, you send it to your data scientists or the decision makers, they look at it, they find some violations and things that do not make sense. You cannot really work on this right away, and you need to push it all the way to sources. So you need to get this, use the provenance, and things that I talked about in the last slide, and push it all the way to sources, push explanation to people that they can act on, and then you come up with repairing actions and repeats. And that never ends. So thinking about data curation as a one-off project, like hire a data curation people, buy a data curation software, and now my data is clean. We tried that, it failed miserably, let's stop doing this. And if you're not using data curation as part of your data production, there is something wrong. You cannot basically afford to curate data, do business as usual, and every now and then clean your data. That approach has proven invalid. And the last word is about how to use users and users in the loop. I am not aware of any fully automatic data curation or data integration project. Not because the machine is not there, the machine probably can come up with a lot of suggestions, but also nobody would trust the machine to change things haphazardly without validation. So at the least, users are involved in validation, but our experience showed that they are involved in every aspect of the problem, from training data generation, to validating rules, to validating models, to validating clusters, to author more models and more rules, to look at the final reports, to suggestions of provenance that should be added to the metadata and repeat. The trick is to realize that there is not only one user, and how to address the right user with the right question. In any organization, you have your data scientist who understand statistics of R and other things, but you have the IT guy that knows how to store data, where it is, how to author a script that actually work in the cloud and will not break, how to provision a stack with mesos and this and that, and with the dependency work, and they have to be involved in the decision making. But most importantly, the stewards and the domain knowledge that have no tolerance to sit in front of a computer and tell you label one at a time, but they will give you rules and will give you resources. So we suffer from that. I'm going to leave you with a couple of screenshots from our integration with the user, just to show that sometimes we need. So this is a screenshot of Tamr when we consolidate suppliers. So for example, these are the records coming from all over the place, and then the machine start to suggest here kind of a schema and an integrating schema and integrating clusters of the data. But what's important as we communicate with the user about these clusters and these pairs, think about this as a conversation. So if you look here, you and Tamr agree, you and Tamr disagree. And that's something that the users would love to see and interact with. It's not simply red and bottom, it's like a radio bottom or anything like that. It is a conversation where I tell you why I'm disagreeing with your rule, or why you have no clue where this came from and we think they're a match because of that. But also when you have a rule, we disagree with you and maybe you should revise your rule or tell us where we went wrong. And without this, you have no hope of getting something deployed, at least in a massive scale. At least that's our experience. So I'm going to leave you with some kind of important thoughts about at least our experience on using something very effective, like all machine learning tools and the automation in a hard problem like data curation, and why we can actually make progress with it. Engineering and plumbing is 80% of the exercise, so this is something we all know. It's about stop trying to find like a monolithic system that will help you do the data curation once and for all, and create pipelines that are repeatable is what's the most important thing. So for example, feature engineering, training data management, managing scale via blocking and hashing and others, explain and the ability to roll back and engaging the user at a high level is super important, super effective to make progress. And the most important, usually overlooked problem is continuous problem management to make sure that you're actually converging with whatever you built. So I think I'm going to stop here. That's okay.
Perfect. Are there any questions for Ihab? I'll ask that to everyone online as well. So I'll be watching the chat if there are any. Hey, Joseph.
So a lot of what we talked about today is to do with what you could argue is almost a static use of data that ends up in Tableau or data that does some reports. And as you mentioned, the people that are eyeballing those reports and that are detecting anomalies are far removed from the generation of data. And you see examples of taking, say, the ERP system and the purchasing example and surfacing those errors and those disagreements in the ERP system, so the poor purchasing clerk who is putting in an order or generating a PO can address it in the flow of their work, as opposed to the data.
Sure, it's a great question. I think, let me repeat that and I'll flip it back to you. So I think Joseph is talking about the consumption of curation in general. Like for example, there are multiple ways of doing this. One of them would be in a very proactive way. While I'm doing things, I can tell you that this will generate an error later in downstream. And when I find something erroneous in the downstream, can you push it upstream where you actually authoring this data? And the short answer is not really. We don't have something to do that. Right? We have a lot of ideas how to do this. When I say we, means the community, like working with data. But the problem with this, that it's a different problem, which I talked about data integration today, but there's a problem of system integration as well. How to make a stack of very different systems talk to each other, which is very specific. So we're not solving that problem. Instead, people create another island where all this data is, and you have to go and query it outside your pipeline, because it's a lot easier, as opposed to figuring out the API between the system and that system and push it there as an alert and modifying the experience on your ERP system. So what we do is we push all of this in this data governance tools that will allow you to register what data source was used in what analytic, by whom, run what pipeline on it. So when something wrong, at least I can query that and I go back and I do debugging and such things. But that full automation in terms of provenance has still a vast open opportunity for most ideas and startups.
So we just have one question from online. George is wondering if there are any other players in the field besides Steam.
Of course,
Is there competition?
so the field of data prep and general data curation is not a small field, and there are multiple. For example, we just did a webinar with an important company in the field as well, Trifacta, because also the academic connections between us and Joe. And example like Paxata, Trifacta, Platforma, and many others are after this data curation pipeline, how to build scalable data integration tools to help data scientists making sense of their data. Now, the focus can be very different. Trifacta focus more on transformations of a single source, interacting directly in the visual with a specific data scientist, while Tamr focus more on the enterprise-wide, the piping behind the whole thing, and how to make sense of the holistic view of all the data sets together. So I think for any kind of a massive project, it's unlikely that you're going to see only one player in the whole organization. Our customers often have 3-4 vendors in to solve their problems. So they focus on different aspects. They have different strengths. We think that data curation, data prep, and schema matching and cleaning are a little bit untapped kind of territory because it's hard and the learning curve is slightly steep. And we're happy that we're covering it, both in academia and in team.
Any other questions? Well, thank you so much.
Thank you.
Yeah, that was fantastic. So we have a couple more events coming up. On Thursday, we have the Fields Institute simulcast. Thursday this week, which will be here from 12 till 2. Lunch is provided, so feel free to sign up. You can join us for that. The next event in the webinar series is June 14th. That will be with IBM. And the topic of the June 14th event is designing for disruptive thinking. So we'll send out a link to that probably later today or tomorrow. One other note, if you have a chance, and if your company is using open data, we'd love if you could fill out our OD 150 survey. John's at the back there with a laptop, and if you fill it out, we have free t-shirts. So we encourage that. But anyway, thank you so much for coming out.